So in light of that, that's also one of the applications that's been promoted for quantum computers, for actual quantum computers. So where does that kind of leave us in terms of, is that still going to be a fruitful area for using quantum computers? Are classical computers kind of catching up? So that was one question I thought of. So maybe we can start off with Mike on that one.
Yeah. This is actually something we were thinking about because I think I can say this, we were working with IBM where they've been using this technique called zero noise extrapolation where they have some somewhat high depth circuit that they run on the quantum computer and you can measure expectation values. In the case where you can compare against something exact, it's correct within 50%. Then the idea of the zero noise extrapolation is they artificially add more dissipation by basically running the circuit slower, and then they can controllably add more dissipation and then extrapolate in this, whatever the dissipation and decoherence is, and then they get extremely accurate results, actually. It was pretty surprising. So, I mean, my intuition is somehow there should be a matrix product or tensor product way of simulating exactly that dissipative dynamics. Like we should do something like what Tibor was talking about, where you artificially introduce this gamma, and then we should be extrapolating the noisy dynamics. So I'd like to see how well that works.
Did you say that in the quantum computer they add a amount of dissipation that they know?
Yeah.
And what the quantum computer outputted was very close to.
Yeah, so after extrapolation, they can't make their quantum computer any better, but they can make it worse in a controllable way. So they'll do like 5 different levels of dissipation and then just linearly or with an exponential extrapolate it. And then it gets very, in the regime where you can verify it, it gets very accurate results. And then they can go to a regime where pure state matrix product or tensor network methods wouldn't work. I mean, you'd need bond dimensions of 1 billion or something, but this extrapolation still gives the right result. But maybe using something like the dissipation-assisted operator or whatever, like artificially add decoherence and see if you could do the same extrapolation trip. Because the extrapolating in bond dimension I don't think will work, but maybe extrapolating in noise would.
So is that something in the IBM simulation you're talking about, that's something one-dimensional as well? Or that's
it's like a 2D quench of a transverse field Ising model.
Okay.
And then they can show at fairly late times that very complex operators are like correctly captured by this expectation values for like a weight 17 operator or something.
Because relating to the question is of course an aspect of dimensionality, right? Or the community is making major progress and indeed reaching longer times and clever new schemes, but mostly for one-dimensional systems. Which is not the limitation that a quantum computer would have.
I mean, so that that could tie in some of the topics we saw already together a bit. So we saw some schemes to go to longer times, and we've also seen some schemes to do some amount of time evolution in 2D now with, say, like ISO-TNS. Maybe it's kind of an obvious point, but could these be fruitfully mixed together? And then maybe 2D is kind of opening up for dynamics that way a bit, possibly.
Can maybe just add that I do think that it is important for tensor networks to put boundaries and limits on where one should search for a quantum advantage. So I do believe that it's important to not utilize quantum resources for things that can be done classically, and to get a much better idea of what type of problems should be put on quantum computers once they exist, and what types of problems are better dealt with on different architectures, different types of hardware. And I think that tensor networks are an excellent tool for contributing to that question and allowing in the future to really make a distinction between different types of problems and where they should be run.
So my background's not at all in tensor networks, so this is kind of like, I work on building quantum computers and thinking about how to use them. So you guys are in some sense the enemy, right? It's like the better you do, the harder the problem is. And I'm both like encouraged and discouraged to see the progress in 1D time evolution. I mean, I think those ideas are really neat. And I guess one thing that occurred to me is, I've seen like there's a lot of impressive work here looking at like, do you get 4, 5, or 6 digits of precision on some hard to compute property? And I think one thing that's often not appreciated is that in quantum computers, a lot of what we obtain at measurement is through sampling. And so there's large error bars from sampling. And so getting 6 digits of precision, if it requires you to run a calculation, 1 over, or a million squared times, 10 to the 12 times, that's never going to happen, right? So one question I always have is, what are the problems that tensor network techniques can't even get you, 2 digits of precision on? I mean, are there problems like that we care about? And I guess I'm not really clear, so I wanted to ask the question to the audience.
It's a good question for the room. So someone have a thought about that question? I think it's a very good question.
Background is also not in quantum tensor networks at all, but I think we can think about ray events. So if you think about things which happen with small probability, then like you have a global state, if you think about this as a probability distribution, there are particular things which happen with low probability. You start computing for these things using like Monte Carlo. They never appear at all in your simulation. You start computing for these things using simulated tensor networks on a classical computer. You are cutting off with your bond dimension. So you are perturbing the tensor. You are perturbing the probability distribution. And then ray events, you are perturbing them too. So to obtain good recovery of ray events, you need very high bond dimension. And this also slows you down on a classical computer. But on quantum computer, maybe you don't have this problem because you're computing the wave function and you're projecting this on a circuit which represents your ray event. And maybe by this you can extract it better than we could in classical domain. I'm not sure if it makes sense.
So maybe another point that was brought up related to what we can do with tensor networks is why does it become hard, or why does approximation become inaccurate, right? And I think there was already a mention of 2 different factors. One has to do with science, and one does not, right? So the fact that the hardness that comes from science is, in my mind, one thing, and then you have the sheer combinatorics that is another thing. So if you, for example, just contract a tensor network to a scalar, even if there are no minus signs, this can be a very hard problem to approximate. And so one thing that I would like to see clarified is to which extent can we push this, and to which extent we can push the fact that we have to add positive and negative numbers, and which one of the 2 is the most limiting. And there's already partial answers to these questions in Garnett and Johnny's paper, where they controllably add negativity to their tensor networks and see that very fast the approximation becomes basically very bad. But can we push back somehow? Can we maybe re-gauge the circuits that we're trying to simulate and push the negativity somewhere, and then try to circumvent these things, these problems, at least partially?
What was the context Garnett was looking at? Was it the environment of a PEPS or a different?
No, it was, literally, if I remember correctly, you write a tensor network either with a geometry or a random graph, and you fill with random entries the tensors, and what you're doing is with a finite probability, you add sign, or rather maybe you pick a uniform distribution and you make the boundary more and more negative, or something like this. But basically, you have a controllable way to add negative numbers in the tensors.
So is that using these generalized loop So that you have an exact reference, is that adding signs in these states that Gardner talked about this morning, these generalized loop states?
No, it wasn't about the loop states. It was a different. I don't know if it's in the same paper, but the benchmark was very simple. You take an arbitrary graph or an arbitrary tensor network. You fill the entries of the tensors with some by picking each one individually from some probability distribution, and depending on whether that probability distribution includes negative numbers or not, you see a very different behavior when you approximate, when you truncate. Right? So basically, when you have, I think the bottom line was, even if you have a little bit of negativity in the tensor networks, then your approximation already becomes bad.
There's one point that I wanted to add, and this is one of the questions that I'm always asking myself is, in nature, so don't look at quantum computing for the moment, we usually see properties of systems that are pretty much robust against kind of small perturbations of Hamiltonians. And they must really not depend on the exact details and all the microscopic parameters, because otherwise they would probably never manifest. And so the question would really be, what type of approximation in tensor networks keeps those robust features present and disregards the things that are not really robust? And to some extent, I'm not always sure that these kind of highly idealized models really pertain to those types of physics that one actually sees in nature. And for me, that would be a kind of important question to find out, can you actually find approximation schemes that target robust features, robust faces, and kind of not fragile and kind of tightly balanced properties. The exception, of course, is quantum computing, and that's where you would probably want then to use a quantum computer rather than classical one.
I guess the difficulty there is if the problem is ground state search, the fact that there's first order phase transitions in nature means that in the end it does come down to like delicate energetics. You can have many competing phases which are entirely unrelated that differ in the fourth digit in energy. And so it does come down ultimately to like how accurate can the tensor network be? If you want to know what phase of matter is a Hamiltonian in.
Yeah, but the fourth place digit in the energy is still a macroscopic change, so it's still a kind of pretty robust feature, kind of given the system size you have. So, it's everything. It must not really depend on whether the outside temperature is 20 degrees or 21 or so. So it will have this kind of inherent robustness in it, in order for us to be able to see it, to measure it, to actually utilize it and to make it functional.
Can I make a comment here on a slightly tangential point? So we've seen these new ideas for evolving for long times, and they're based on robust physics. They're based on the idea of the eigenstate thermalization. They apply in other dimensions as well, actually. But these improve our classical simulation. To what extent can those sort of ideas improve our quantum algorithms? And where does the quantum advantage remain?
Well, that's an interesting question, I think. But here, I think the point is really, the way I view this is, the more abstractly a problem is encoded on a quantum computer, the further away it is from the kind of physics that is described by the qubits themselves that you use, the more likely it is that this robustness will not matter anymore. So if you do simulations that are close to what is done in nature, you probably can win by that argument. If you want to do a portfolio optimization of some financial things, you probably won't, because you're going to look at very different observables from what we in physics want to look at. But I have no proof for that.
Question is, if one can find something that is hard for tensor network, but can be done by quantum computer, right?
Yeah, that would be an interesting problem, yes.
Yeah, I think if any of you know that in principle, we cannot know if two paths are equivalent.
But can I don't think a quantum computer could either.
So you know that the PEPS is related to the tiny problem, which is equivalent to the hot problem, right? Yeah, but there is a recent article, maybe some of you already know, called the minimal canonical form. That means that says we can iteratively to gauge fixing the two-dimensional PEPs, and that gives a very good result numerically for most of the cases. So this is quite a contradiction with. So if precisely we cannot see if two PEPs are equivalent, but numerically it is something very easy to do.
Well, I guess it's a matter of guarantees. Like there can always be a much larger length scale where you all of a sudden see.
Yeah.
Also, I think that result really requires that, like, states are equivalent for all kinds of different graphs in which you can contract them. So, like, if you really have a PEPS and then you think about just like an infinite square or some putting them on a torus, having some periodic boundary conditions, but that result stating that these two states are equivalent if and only if they have the same canonical form. It really requires that I mean, you consider all types of graphs with arbitrary topology, and then indeed, I mean, then you have this if and only if condition. But I think you can just have two different PEPs or two different PEPs tensors which give you the same state on the torus,
Yeah.
and which would not have the same canonical form, which would have different bond dimensions and.
But Michael, as our enemy, declare enemy, would you consider being able to check whether two PEPs are the same or not an application of quantum computing, or that's not what you had in mind?
It's not what I had in mind.
Okay, surprise. Yeah. So did you mean something that you could sell to investors?
Yeah, believe it or not, it's pretty far from my mind. I mean, my background's in many-body physics, so I think, like, what I would love to see quantum computers be capable of, I think it probably is their best hope, you know, in the near term, is to solve problems that people actually want to know the answer to in many-body physics.
But that would be, say, two-dimensional, ground states in 2 dimensions or 3 dimensions if PEPs can get close to 2. Wouldn't that be already great?
I think that would be great.
Okay, so that's the answer, no? I mean,
well, but I don't know what, I mean, so what kind of accuracies do you think people can achieve in computing ground state energies with PEPs? I mean,
but I think in 1 dimension we get silly. Oh, I can get 6 digits. Oh, I can get 7 digits. Right. So what, right? It's go and do 2 dimensions.
Yeah, so that, how
to normalize your ego for a bit, yeah. What's that?
And how bad is it in 2 dimensions? Like I see arguments about, like, you know, or there were these, you know, over the last 15 years, arguments about, you know, like, what type of order do you find, or what variational kind of class of states wins out for some frustrated spin model or something like that? And these arguments are settled often by, like, I think the 3rd or 4th digit in the energy, right? And so it's not clear to me that, like, there's really a role for quantum computers in answering questions like that.
I see what you're saying when the answer depends on so many digits, but I don't know that. I mean, there might be qualitative questions that have not been answered yet.
Yeah.
Which one?
I hope.
In 2 dimensions?
Yes.
I would go and ask Philippe.
I think there are no, I think even, so a qualitative question, I think even with mean field, you almost get it always. So let's face it. I mean, we are trying to do precision things here.
So that's interesting, because when you go to condensed matter physicists, right, they don't think that they can generically solve problems.
No, indeed. Gapless phases are hard to, I think gapless phases typically are hard to pinpoint and understand if there are finite effects, but this really requires precision. So 5, 6 digits, that's the point. I think.
Because it's gapless?
Yes.
But maybe you have some protection that makes it gapless.
But also, if you have, like, competing orders, it's very likely that also system size will be a very relevant aspect.
Like
I agree that once there is competing orders, it's a precision thing.
Yes.
I agree with that. But I don't know that you need to go. I mean, we saw time evolution simulated in 2 dimensions today, right? There were, like, a few time steps and we were lost, right? So you know.
Yeah, no,
Try-
but
try
time
to-
evolution I think is different. So exactly, you were talking about ground state 2 seconds ago.
Excitations on top, seeing dynamics on top of ground states, right? Low energy physics, which involve time evolution.
That's different. I mean, it's. I guess low energy excitations will be more feasible with tensor networks than like global.
Okay, so let me
quantities,
refine it. I mean, small but finite energy density.
Okay.
For large systems, right? Where tensor, you have a volume law of entanglement, and you still have enough sufficiently small energy that you are not in the middle of your, that you don't have a completely random state, right? So do time evolution in that regime. Finite energy density, it's finite but the small energy density. Throw away all the tensor network techniques on the spot and start thinking, I would call Andreas and say, hey, how large can the system be with exactly?
For example, we did some spin wave evolution exactly in that regime, small quenches, and you get amazingly good results compared with the MRG short time, but then you can go to infinite time. And then you obviously don't know if the infinite time is good, right? Because you don't have the MRG there.
Are you talking about 1D again?
Yes, 1D.
Okay,
but I think that 2D, so from that respect, the 2D spin wave works equally well in that respect. So I don't have the PEPS code to check the evolution, but I expect that indeed. So there are very powerful, almost analytical tools to give you an idea of what's going on. So, and then the question is,
but maybe we're just asking the wrong community, right? We are a specialist in the IC model plus variations of it, and especially variations where we can do something. And then we should go to the condensed matter physicist and say, hey, what problems would you like to see solved?
I mean, there's
You're asking the wrong people.
Like the Kagome spin liquid Heisenberg model on the Kagome lattice. Like, I don't think it's still yet resolved whether it's a gap spin liquid versus valence bond, and those would have like universally different behaviors at long distances.
But Mike, this would be an example of high precision, right?
Because I have sort of a thought
well, there's
about.
still like there's universal distinctions that in principle, if you're in the right phase, you'll have different power laws, at large dimensions or large distance. But I guess making sure you're in the right phase is kind of a precision thing.
I thought about that example of the Kagome. So I wonder if that's a good example that ties together a few comments that have been made about what precision's needed, will quantum computers catch up, and also your comment, Dieter, about things being robust, Like, because if you kind of unwind back to why were we studying the Kagome anyway in the first place? I mean, I'd like to hear from other people, but I thought one of the premises was that it was supposed to be one of the simplest models to show possibly a spin liquid. But then I would argue that it's not really simple, like that wasn't true. Like it's simple to look at on paper, like the Hamiltonian is simple looking. But the ground state manifold apparently is not really very simple, actually. But meanwhile, if you actually could realize it in nature, like say if Herbert-Smithite really is close to it, it's at some finite temperature. I mean, it may be very small, but some finite temperature. So if we had better methods to say do low but non-zero temperature, say with PEPs in the future or with quantum computers, would these now be much easier targets? Like would our methods already be good enough if we just reframe the problem at kind of finite temperature and then say our job is not anymore to resolve these tiny competing states?
It seems I mean, I think there'd still be like even at finite temperature, there'd probably still be first order phase transitions between some of the different phases. So it's probably just as hard at low but finite temperature.
So still could be just as hard, just for different reasons.
I think so, because I think like if it's the valence bond pattern versus one of the spin liquids, that distinction would still remain at finite temperature.
So one comment regarding that, quantum computers don't work at zero temperature, right? So they have some finite temperature where you can still see some quantum effect, but you are always some thermal population. So I guess they're in the regime where you don't have exactly zero energy density, strictly speaking. And that's the regime that is complicated for PEPs.
Yeah, I mean, it's hard to imagine quantum computers working well in a regime with any, finite energy density. I mean, they don't really work. It's not just zero temperature is the problem. It's any, thermal equilibrium that's the problem in some respect, I think. I mean, so just solving, out of equilibrium dynamics is a much more natural problem, right? Which is part of why these techniques that kind of kill 1D dynamics are somewhat discouraging, I think, from the standpoint of quantum computing. Although maybe maybe there's corners there that haven't been solved, or you just have to go to higher dimensions, or maybe you have to find physics you care about that relies on like non-k-local observables, so you can't use these techniques or something. Maybe there's sampling problems in 1D dynamics that are still hard.
I guess we should clarify, like most of these techniques work by throwing away complicated information. So if you ask, what's the expectation value for a weight 23 operator, you won't get the right answer. I mean, in principle, if you had error-corrected perfect quantum computer, it could compute that with perfect ease. It's just, it's not clear whether you're in the regime where you'd expect a weight 23 operator to be correct.
Sure. I mean, I agree. Like a quantum computer will have difficulty with that too. But I mean, if the techniques that we heard about, yesterday can, extend the time evolution of k-local observables to a very long time. I mean, I guess it's more a question of which is worse, right? Like the bond dimension truncation effects you get if you just try to go to long time for some more complicated observables, or the noise effects that you get on a realistic quantum computer. And I don't, like, which one is going to be better or worse in the near future is not really clear to me, I guess.
It's like a near-term question. Like if we assume quantum computers will eventually work, presumably measuring one of these very complicated operators is a case where it would be, you'd have advantage. Like,
I think there's one other thing that people should consider, and this is that in many of the actual materials that quantum computers and tensor networks and so on try to deal with or try to actually make predictions of, the model isn't even known that accurately. So you don't know what the microscopic model is. So there is first a question, to what extent do you need precision and all of this if you have the wrong model? And so there is, of course, in terms of practical usefulness of tensor networks and quantum computers for materials design or condensed matter physics, real condensed matter physics. In that sense, there is this additional question, how do we actually model these systems or get models that one can trust and can solve, and most of them don't make predictions about what happens in the lab. I mean, a condensed matter colleague of mine always says this is like a jungle. So.
Yeah, this is a sort of detailed question, but do we actually have a like-for-like comparison between the infinite temperature correlation functions that were the basis of the methods we heard about yesterday and something similar done on a quantum computer? Or, I mean, this comes back to the sampling question, I guess, about how you would actually do this in practice. So the talks we heard about yesterday, we're talking about infinite temperature correlation functions of local observables. And I guess the question is, did anybody try? I guess you would have to prepare an ensemble of initial states and evolve them, and then there's an averaging issue, and I just don't know whether that issue's been addressed to make the comparison.
Yeah. So
Oh, yeah.
we actually worked together with a group of Rainer Blatt, on an analog simulator. But there the problem is always that you sort of naturally have noise in the system. So you will be able to extract the diffusion coefficient just like we heard in the talks, but it will be at some finite noise strength. So in order to sort of reliably extract the zero noise limit, you would have to find some sort of scheme in order to extrapolate, just like in the numerics.
Actually, the finite noise also makes those truncations correct there as well. So
right.
It may be a feature, not a bug. So.
Do we think that quantum computers will ever compute ground state properties, or is it only dynamics they're useful for?
That's a loaded question. I guess.
Can you ever do a variational computation without the sampling costs and so on?
I mean, I suspect the answer is that if you let your imagination run wild and you think, okay, I have an arbitrarily large, and well error-corrected quantum computer, I would think the answer is yes. I mean, like all the problems that you face with variational algorithms come not really from the quantum computer, but from the fact that you were motivated to try to find a variational algorithm in the first place, right? Which you had to do because the better algorithms you can't run on realistic computers. So I would think the answer is yes in the long term, but I'm personally pessimistic about